Mukasei niita.
Mukasei ni ita. Does that mean have we gone to Mars yet?
Yeah. Nah, sort of.
This episode is all about Japan. And we're quite excited because we had this trip planned before the pandemic struck, and then it was postponed and postponed and postponed.
But a while back, we finally got to go. And wow, we were really amazed and inspired by all the things we got to learn.
Things that we're now more than happy to share with you guys. My name is Marcus Pettersson.
My name is Susanna Levenhaupt.
And you're listening to Have We Gone to Mars Yet?
JAXA, Japan Aerospace Exploration Agency, is the Japanese equivalent to NASA, or ESA. Professor Masaki Fujimoto is the Deputy Director General at JAXA's Institute of Space and Astronautical Science. We met up with him to talk about a few of JAXA's space missions, all of them small steps towards the long-term goal to land on planet Mars.
We talked about one sample return mission to an asteroid, one mission to Martian inner moon Phobos, and of course the recent SLIM mission to our very own moon.
But before we get into all that, Mr. Fujimoto, can you please tell us about where we are right now?
So you are in the southwestern edge suburbs of the great Tokyo area, Sagamihara City. That's where our campus is located. And this is an institute where we plan, design, build, and then launch space science missions. And most recent one is the Hayabusa 2 mission that returns samples back from an asteroid.
So you do all the research, planning, and building here as well?
We do work together with the industry, of course. But basically, we really take care of the space missions because space science missions is really, really special. So you really need expertise to make a successful mission, and that's what we are responsible for.
Okay, so tell us about the Hayabusa 2 mission.
Yes, it's an asteroid sample return mission. The target asteroid was Ryugu, one of the primordial asteroid. And what I mean by primordial asteroid is the small bodies born in the outer part of the solar system. Here's some remark. If a planet is born in the inner part of the solar system, it is born dry. And Earth was born in this inner part of the solar system. So it was born dry. It was born without water or organic materials. So if nobody brought water or organic compound to Earth, our planet would not have been habitable at all. So who brought water or organic compound? We think it's somebody like Ryugu, small bodies born in the outer part of the solar system, primordial asteroids. So that's the reason why we dare to go all the way to Ryugu, get the samples from its surface, and return the samples back to Earth for a detailed analysis utilizing facilities on the ground.
Where is Ryugu? Where is it located?
Okay, I said Ryugu was born in the outer part of the solar system, but now it's coming to the inner part of the solar system. Its orbit is between Earth and Mars. So that means that it was born in the outer part of the solar system, but now it's closer to Earth, which means that it's a very convenient primordial asteroid for us to return samples back from. And there are many of them in the main belt asteroids, that's like beyond Mars, in the position between Mars and Jupiter. But going all the way to main belt and returning samples back, that's kind of too much. So it's much better that if you find the primordial asteroid that's much closer to Earth. And now we know there are maybe only 3 of them. There are only 3 sample returnable primordial asteroids, and we picked one of them. NASA picked another one, and there's one remaining. But the one that's remaining is a tough one. It's not easy to go there and explore the system.
What is it that makes the third one difficult?
Well, it's a binary system, so it's not just a single body. It has 2 bodies, and one smaller body is rotating around the other body. And to explore such a system is kind of a headache, especially if you want to land on the surface and get the samples back. It's a complicated issue. When it comes to material science, you better get the samples and analyze them to tell the truth, to know the truth. So you can visit those asteroids and make remote sensing observations, but that's not going to satisfy your appetite. You better get the samples from its surface and bring them back so that they will be subject to very detailed study utilizing all the analytical machines available on the ground. So that's why we're interested in returning samples back from primordial asteroids, not just exploring them. Another point about these asteroids is that it's better be smaller so that you can get the samples relatively easily from its surface. If it's bigger, the gravity will be stronger, and then getting samples back is not easy. If the gravity field is small, you can do the touch-and-go sampling, which is relatively simple. So we are fond of smaller asteroids. And these two asteroids, JAXA's target asteroid and NASA's target asteroid, they are smaller than 1 kilometer in its width. So it's really tiny. So it's good for this touch-and-go sampling. But on the other hand, it means that you don't know nothing about it until you get there. From its spectroscopic features, you can tell that they are primordial asteroid. You know that it's there, but that's all you know.
So you went there and you touched down and got your samples. And how much did you get?
Yeah, we got 5.4 grams in total. And if I tell the number, people say, wow, such a tiny amount. But if you think about all the technology we have on the ground, all the machines for the sample analysis you have on the ground, 5.4 gram is a huge number. Actually, the minimum requirement was only 0.1 grams. So we have 50 times more than the minimum required, so it's a big catch.
What did it consist of when you did the analysis?
Already through the very first rather simple steps, we have confirmed the existence of hydrated minerals, basically water, and also organic compound in the samples. So we are already very happy at that moment, thinking that we really went to the right target asteroid. And then through the initial analysis, we learned a lot, like more than 20,000 organic molecules contained within the samples. So people talk about what are the starting materials for the chemical evolution towards the emergence of life. Maybe the answer from Ryugu is that maybe we have more than enough to start the chemical reaction from.
And could you give us the timeline here? When was the mission launched and when did it return to Earth?
We launched in December 2014. We arrived at the target asteroid in June of 2018, and we struggled for about almost about 2 years. And then we left the target asteroid in November 2019, and the sample return capsule landed in Australia, Woomera, in December of 2020. So it's a 6-year journey in total. And at the asteroid Ryugu, we spent how many years? Almost like 1.5 years, scratching our head how to get the samples from the surface. But we managed to get the samples twice. And so it was a very big catch, not only in terms of quantity, but also in terms of quality.
And what was the problem that you met when you got there?
Yes, as I said, Ryugu is a tiny asteroid. We knew nothing about it until we get there. So when we get there, we found the surface to be super unfriendly. It was rough everywhere. But we have to perform the touch-and-go operation, which means that the tip of the sampler horn must touch the surface without other part of the spacecraft being hit by rocks on the surface. But there were no, big open land on the surface of asteroid where you can land safely. So after arrival to the target asteroid, we had to invent a new way of controlling the position of the spacecraft much more precisely than we had assumed. And that way we can navigate the spacecraft more precisely and then land onto a much smaller spot than we had thought before. And we managed to do so. We managed to develop the technology within half a year, and we got the samples from 2 areas on the surface of the asteroid. Kind of funny part of this story is that originally we had the plan to land on the surface 3 times. And for the first 2 times, we were serious about planetary science, so we get the samples for sure. But at our institute, it's a nice combination between scientists and engineers. And the engineers always want to embed something new so that that can be the trigger for the next mission. And for this Hayabusa 2, the plan for the third touchdown was to utilize a new technique. And we didn't know whether it's going to be needed or not. But they knew that with that new technique, we will have a better precision in controlling the position of the spacecraft. So engineers wanted to sneak that opportunity into this mission, not knowing whether it's needed or not. But then it turned out to be necessary from the very, very beginning because of the unfriendly condition that we were facing. So I think it's really funny that engineers, engineers trying to enjoy something new turned out to save the mission.
And you got your 2 samples. Were they different in any way?
So thank you for the question, because we did 2 samplings. That's already bold enough. But between those 2 samplings, we dared to perform an impact experiment. So impact experiment is something like you shoot the surface with something like a bullet, and you create the crater. You make a artificial crater on the surface of the asteroid. The purpose of this impact experiment is to learn about the crater formation process under the microgravity. That's something we don't know. Well, crater is a big source of information for planetary science, so we better understand the formation process precisely. But all we know about crater formation process is coming from the moon or our knowledge on Earth, under the strong gravity environment. So we knew nothing about crater formation process under microgravity. So to learn that physics, we performed this impact experiment, producing an artificial crater on the surface of the asteroid. And that turned out to be very successful. At the same time, formation of a crater means that you are excavating subsurface material onto the surface. And the way we get the samples back is that it has to be on the surface. Otherwise, we cannot grab anything. But now, subsurface materials, which is more fresh, which is less space weathered than the surface materials, now they're on the surface. So why don't we go and get it? So the second touchdown was not just a second touchdown, but it was a second touchdown intended to grab subsurface materials that was excavated thanks to the very successful impact experiment.
Did you find something that you did not expect to find on Ryugu?
Yes, there are many of them. I only mentioned organic compounds so far. So let me tell you what I'm really excited about. I think we find the evidence that Ryugu was originated at Saturn's position and then migrated to the inner part of the solar system within 5 million years after the formation of the sun. And that's something we can tell from, by combining signatures we see in the samples. There are 2 things that it means. First of all, why is it migrating such a long range distance? It must be something big that made Ryugu. Ryugu is passive. Ryugu itself doesn't really do anything, so there must have been somebody else who made Ryugu to migrate as long distance as this. And it must be Jupiter. Well, Jupiter, that's the biggest planet in the solar system. So what this implies is that Jupiter must have formed within 500 million years after the formation of the solar system disk. So Jupiter is the biggest planet in the solar system, but yet it seems that it's the first to be formed within the solar system. And that's something really, really interesting. And then it also means that how dynamical the early solar system is. I kept on saying that it's somebody like Ryugu that brought water and organic compound to Earth to make it habitable. But through what process? It's as highly dynamic as, Jupiter playing the big role in shaping the whole solar system. And then the question is, our planet being habitable, is it luck? How lucky is it to be like this? Can it be a little bit different? Can it be, if Jupiter behaved a little bit differently, our planet would have been a very different world, and maybe we're not existing today. I don't know, maybe it's not a scientific question, but it really makes you think.
So let's talk about the MMX, the Martian Moon Exploration Mission. Could you take us through the journey from launch to returning to Earth?
So we recently had the problem with our launcher, so the dates may change, but the original plan was something like this. We launch in 24 and arrive at the Martian system in 25. We will stay there for 3 years. And during that 3 years, we will land on the surface of Phobos and then perform the sampling on the surface of Phobos. And then after 3 years, spending 3 years in the Martian system, we leave the Martian system and come back to Earth in 2029. Release the sample return capsule to Woomera, Australia. It's a desert area in the middle of Australia, where we'll recover the sample return capsule and bring it back to the facility in Japan so that we can open up the capsule without any terrestrial contamination. And then we will get the samples in hand, 10 grams at minimum, hoping to get more. And it must be even more exciting samples than we got from Ryugu.
And why do we want to study the Martian moon?
Well, if you think about the position of Mars in the solar system, it's really sitting at the gateway position between inner solar system and outer solar system. And at this moment, we are really interested in material delivery from the outer part of the solar system to the inner part, like water or organic compound. And now Mars has two weird moons, Phobos and Deimos. They really look like a primordial asteroid. So our idea is that Phobos may be a captured primordial asteroid that was making on its way from outer part of the solar system to the inner part. Then why don't we get there and get the samples, and then we can learn more about this connection between outer solar system and inner solar system. But does that mean that we know its origin? We know the origin of Phobos. We know that the origin of Phobos is a captured asteroid. We don't. There are other camp of people arguing that Phobos was created through giant impact on Mars that ejected debris from the surface of Mars into space around Mars to form a disk. And within that disk, Phobos was created through accumulation of debris. But we don't know the origin of Phobos. So when we get the samples from Phobos, we know the origin. It may turn out to be a captured asteroid. It may turn out to be the impact story. But even if it turns out to be impact story, I'm not worried because it's even sexier. Because the samples we get from Phobos means that it's an ancient Mars samples, and that's really, really exciting.
So Deimos is not as exciting as Phobos?
Yeah, very good question. Phobos is the inner moon, and Deimos is the outer moon. Space engineering-wise, Phobos is tougher to get to because you have to dive deeper into the gravity well of the Mars because it's closer to Mars. So if you are just space engineer and nobody else, you would rather go to Deimos to get the samples from. But as I said, Phobos is closer to Mars, which means that if there was an impact event to the surface of Mars, there will be debris ejected, and they may be sedimenting on the surface of Phobos. So when we get the samples back from Phobos, they may include Mars samples. So the closer you get to Mars, there's a bigger chance that you get more Mars samples. And the reason we picked Phobos than Deimos is this better chance of returning Mars samples by returning samples back from the surface of Phobos. So that's the only reason we're going to Phobos. Other than that, Deimos and Phobos are equally mysterious.
And just take us through the sample catching again, because you also said that you will bring the American rover.
We really want to make sure that we get any samples at all, first of all. So it's nice to have I wouldn't call it a backup system. It's nice to have an independent system. The U.S. system will work as soon as we land on the surface. So on the footpad, there's something like a vacuum cleaner installed, and as soon as we land, that cleaner will work and suck all the surface materials into the container. So we get some samples already, or surface samples already. But then, as I said, we will stay on the surface for 3.5 hours. We can have some room to do something more complicated. And the plan is that we have a robotic arm, and then robotic arm has a range where you can move around. So we try to pick the best spot within the range and push the Cora into that best selected spot. That's what we are thinking now. But on the other hand, we really have to do this complicated. So maybe any samples can be precious. So do we really have to be so picky? I really don't know. But again, engineer likes to do this. So it's not necessarily driven by science, but it's more engineers' desire to do something robotic, robotically sophisticated. So the plan is that you control your arm and pick the spot and push the Cora into that spot and get the sample from subsurface. That's going to be operated within that 3 hours while we are on the surface of Phobos.
What is the difference between this sample return and the return you did with Hayabusa?
Hayabusa 2 went to asteroid Ryugu. Its size was like 1 kilometer-ish. Now, Phobos, it's 20 kilometer-ish. It's much larger, so the gravity is much stronger. Because the gravity is too strong that we cannot perform the touch and go sampling as we did for Hayabusa 2. So for Phobos sample return mission, we have to land on the surface of Phobos for 3 hours, and we utilize a robotic arm to push the Cora into the subsurface to get the subsurface materials. And we also have sampler from the US that will collect the samples from the surface. So because we will land on the surface and stay there for a couple of hours, we can do something more sophisticated than we did for Hayabusa 2, which is a challenge, but at the same time, it's a nice. Well, challenge in English may have a negative impression, but in Japanese, challenge means something, just do what you have to do. And in our culture, that's a positive thing. So MMX may have to do something more complicated, but we take that as a nice opportunity to develop our technology.
We talked before about, in Sweden, we did an interview about the Mars sample return, which seems to us like a way more complicated mission. So how is it that you can make this so much easier?
Yeah, because I think we know what we are. I think that really matters. And it's kind of funny because now I'm really proud of MMX. But when we started to propose this, people asked, "Oh, you're not going to Mars itself because you cannot? Are you going to Phobos instead because Phobos is the best thing you can do?" And our answer has always been yes and no. Because it's yes, we don't have a biggest launcher in the globe. Our launch capability is limited, our budget is limited. But still, through the experience we had in Hayabusa 2, we learned to know who we are, what we're really good at. There is some impactful things that we can perform even through small body missions. So we have been thinking hard how to be smart and strategic. And as a result of this consideration, we came up with the idea of MMX. But at the same time, we were ambitious enough to think that this will be our first step towards our Mars exploration mission. We will perform MMX, but this should be a nice way of maintaining our brand by performing another small body sample return mission, but yet performing the very first step towards our Mars exploration. And we are already start planning our Mars landing mission as we prepare the MMX mission.
When the sample returns and you open it, what is it we hope to find?
Well, it sounds like a ground finale joke, but we have already written a paper on this. I hope to find shigai. Shigai is a Japanese word for a dead body. Well, in this context, it's like evidence of a dead living cell on the surface of Mars. As I said, among the included in Phobos surface samples, there might be some Mars materials included. And in that Mars materials, we are hoping to get some shigai, dead body of living cells, that was on the surface of Mars. That's my biggest wish. So, I'm not just joking. And theoretically, it is possible, but we'll see. And of course, how damaged they are, can we recognize them? That's going to be an interesting question. But somewhere in our mind, we'll have this idea. We'll keep this idea and see if we can find any of them. So, that's my hidden wish.
Okay, so first there was the Hayabusa 2 mission, and hopefully next year you'll launch the MMX mission to Phobos. But how about the SLIM mission? Could you tell us more about that?
SLIM is a very small technology demonstration mission. It will demonstrate two technology. One is the pinpoint landing with a precision of 100 meter-ish. And the other is a demonstration of two-step landing scheme that will bring us to relatively non-flat area. So the idea here is that once you have the pinpoint technology, if you tell the scientist, they will tell you, I want to land here, I want to land here. And those spots may not be flat. Then we better prepare the technology to land in a less flat area at the same time. So pinpoint technology plus two-stage landing scheme are really comes nicely together. So that's the design of having these two demonstration in this one small tech demo mission.
So it's a demo mission to provide launching for future scientist missions and for business as well.
Yes, I think this is the reason that it's a small mission makes it accessible to business people as well. Because if you do something like this with a big mission, who else can do this? It's only the national space agencies. We have the strategy to perform something that's interesting and exciting with small resources, because I think that we are really good at this, and that will enable somebody else to be a part of this, especially the commercial people. So the reason that it's relatively small is based on intention, our intention that, lunar surface and Mars surface for more people, than not only for those people who can launch big missions.
Okay, so SLIM is quite a small mission, but how small is it dimension-wise? Like, how much does it weigh?
It's 700 kilograms in total, but 500 kilograms is the fuel for landing. So it's that much it takes. Moon landing, it's really crazy because the gravity field is so strong. You have to bring that fuel to slow yourself down. Otherwise, you just end up crashing on the surface. So even though it's small, majority of them goes into the fuel to bring it to the surface. And so the more mass you want to bring to the surface, more fuel you have to bring. So that's what I mean by small. So if you dream too big, if you want to say, I want to bring this, I want to bring this, I want to bring this payload to the surface, then you need even more fuel. Getting to the surface of a big body is really, really tough. So you better focus, you better make up your mind clearly that I want this observation. And just bring that payload to the surface. And that's what I mean by small, smart, and strategic mission.
And it does not include any return.
Return is another beast. Return from a big gravity body, yeah, that's a lot, and we haven't got there yet. We haven't come up with a smart strategy to perform a sample return mission from Moon or Mars yet.
If you were to take this technology and do a Mars landing instead of the Moon, what kind of alterations would you have to do to the technology?
So SLIM is really the minimum size mission, but it's really triggering us to think about landing on Moon and then Mars. So SLIM is really a trigger for us to think about the program so that we will eventually land on Mars someday. And so we have MMX. We will go to Phobos, and people ask, what about landing on Mars? And now I can say, yes, we do have a plan, thanks to SLIM, because without landing on Mars, you don't. I think it's dreaming too much to talk about Mars. But SLIM has started a lunar landing program, and a follow-up to SLIM will let us have experience on the surface roving machine, the rover, which we have a plan to bring to Mars. And when it comes to Mars landing, we will perform it in a very different way from what NASA does these days. I think even when it comes to Mars landing, we should pursue a way of performing it with small resources. And we don't bring a huge rover. The biggest rover we will bring will be like 100 kilogram-ish. But still, we think if you are focused, we can perform nice science. So again, like we did for Hayabusa 2 MMX, we have our own way of making access to the surface of Mars, making a lightweight access to the surface of Mars. And I hope that will make that available to our friends on the globe, whoever who thinks about getting to Mars, but not without that much resources. Maybe we can cultivate a way, and together we can have a more frequent program of exploring the surface of Mars with more focused ideas.
It really seems to me that you have, like in these 3 missions that we've discussed, that you really have a plan and a focus for JAXA and what you're doing in the future. Because this is an industry where we talk long perspectives. What is the next step after these 3 missions? What do you want to do next?
I think that's really a tough question, I would say. Now, we're always thinking about alternatives. We have been really helped by giants like NASA or ESA. They've been really helping us to come up to where we are now. Through those experiences, we knew that if we try to do the same thing together, we will be the smaller version of what NASA and ESA does, and that's not exciting. So we've been helped a lot by NASA and ESA, and at the same time, we are always thinking that we cannot do the same. We will not do the same thing as they do, so we will always go for the alternative idea. And doing something exciting with smaller resources, smaller assets, has been our style. And we have the confidence that we can punch this way through because we have had that big success with Hayabusa 2, so we now have the confidence that this is what we should pursue, at least for the next 10, 20 years. And then beyond that, what we will do, I really don't know. But the idea I have is that by performing these nice missions in the next 10, 20 years, we can be a sort of a leader for those people who are interested in landing on Mars, but who doesn't have that big money or big capability. But we may be the leader to help them a little bit and form a formation so that together we can explore Mars. I'm not sure if I'm answering your question, but I do have that kind of concept of, a platform that which we build through these missions in the near future that will enable, I wouldn't call less matured, but it's as simple as this. It's not only China or America who have access to the surface of Mars. If that is the case, it's not. I find it sad. Many more people are interested in having access to the surface of Mars, but it looks very tough. But maybe through the series of success in the near future missions, we may be able to establish a platform where smaller countries can come together and perform a more focused mission on the surface of Mars more frequently. And I think that will make our world happier.
How incredibly inspiring to hear about JAXA's line of thinking. I really like the way they plan for the long run, know their limitations, and build accordingly.
I agree. It isn't always about being the biggest actor on the scene, is it? Let the Japanese model be an inspiration to us all.
Absolutely, and we'll soon be back with more interviews. The music you hear in the background is written by Armin Pendek.
I'm Susanna Levenhaupt.
I'm Marcus Pettersson.
Have We Gone to Mars Yet? Is made at Beppo by Rundfunk Media in collaboration with Saab.